Hey there again, folks. We are going to be wrapping up our probability module, except for the very important practice problems, by talking about a concept that is used to help us solve one of the bigger problems in creating these hypothesis tests. And that problem is basically this. We can use z-scores to find relative standing, and we can calculate the probability of those z-scores and integrate that into it. But the original formulas only work for individual scores. In research, we generally care about the average of samples. So remember, here's sort of our problem. Sample means don't vary as much from the population mean as individual scores do. And sample means from samples of different sizes also change in their variability. The more people in your sample, the less it's going to differ on average from the population mean it's used to estimate. So the way that we again try to sidestep that is by creating what's called a sampling distribution of means. Basically, you can think of this as a distribution of possible outcomes for a sample like yours. If you took every single possible sample of the same size as yours from the same population and you put all their means on a distribution, what would it look like? So before we dive into this, just like I said in the last video, the thing to keep in mind here is this is sometimes hard to wrap your mind around conceptually, but the actual solution, the actual change that comes at the end is very simple and very easy to implement. So again, you should understand this conceptually, but if you have trouble with it, there's still time to kind of recap it. And the important thing is understanding what effect it has on our formulas, on our calculations. So here we go. So sampling distributions are, again, a theoretical distribution. We don't actually create them. We use, again, mathematical proofs to determine what characteristics they'd have. In this case, the appropriate theorem that backs up the characteristics of this sampling distribution is called the central limit theorem. We are not going to get into the central limit theorem specifically. Again, not a math class. We're going to use this instead. We're going to focus on how we use this to inform what we actually want to do. So there are proofs of everything that I'm talking about today. They are beyond the scope of this class. They are not something that we're interested in delving into. You're going to have to take it on faith or look it up on your own. So the central limit theorem gets into, again, a lot of higher level math, but for our purposes, the key things it tells us is some of the key characteristics of that sampling distribution. First, even if your original raw score distribution was not normal, even if it was skewed or bimodal or anything else, the sampling distribution will inevitably start to resemble a normal distribution and eventually become a normal distribution as you measure more and more people. At sample sizes at greater than approximately 30, the sampling distribution always follows a normal curve, even if the raw score distribution does not. Now, don't worry so much about why that's the case. We're going to look at some visualized data to start to show you how it happens. But don't think so much about why that's the case as how powerful that is. That normal curve, that universal shape, most variables fall into this normal curve in the population just naturally. But even if they don't, creating a sampling distribution of a sample size larger than 30 is going to create a normal curve. What that means is that we can use the normal curve anytime we measure more than 30 people. Oftentimes when we measure fewer than that, but anytime we measure more than 30, we can again use the characteristics of that normal curve. And again, that really adds to the power of that framework. So it doesn't work the same way for any other descriptive statistic. We could make sampling distributions for all this other stuff. We're not going to. Sampling distribution of means is the one we're doing, and we know that it follows a normal curve with a sufficiently large sample size. So variability changes in those sampling distributions. Again, the more people you measure, the more the distribution kind of compresses, as we'll see in a minute, but the mean never changes. The mean of your sampling distribution is always exactly the same as the mean of the population. The tricky part is you don't always know what the mean of the population is. So sometimes you don't have that information, but you know that whatever the true population mean is, the mean of the sampling distribution is identical. So we'll see some examples of that in just a moment. But here's how we solve that variability problem. Basically, we know that the mean stays the same as our sample size changes, but we know that our variability is going to decrease as we measure more and more people. We'll talk about how that looks in formula form in just a moment. So again, your rule of thumb to remember, the more people you measure, the more variability drops, until at the extreme, if you measured everyone in the population, variability would be 0. Your sample mean would be exactly the same as the population mean by definition. So here's what this means in terms of raw score deviations. So just differences in terms of that original score that you started with before you turned it into z-scores. It means the same raw score deviation becomes less and less likely, less probable with samples than it is with individual scores, and less probable with larger samples than smaller ones. If that's tricky to you, think about it this way. Let's say, again, that first exam that you've taken at this point, let's say that we have an average on it. I don't know what it is yet, but let's say the average is 75%. So that's our mean. And let's say I'm interested in looking at students who are more than 10 points away from the average in either direction, higher than 85, lower than 65. So let's say I drew a random sample of one student and just looked at whether or not they were more than 10 points above or below the mean. Now, the probability of getting one student that would qualify, that would fit that criteria, be more than 10 points from average, is pretty good. Usually a solid third to half of the class are more than 10 points away from the mean, or sometimes even a larger percentage than that. So the probability is pretty high there. But now think about if I drew a sample of, say, 5 students, averaged their scores together, got a sample mean. What are the odds that that 5-person sample is going to be more than 10 points away from the original average? It starts to drop a little bit because people who have unusually high scores are probably going to get offset by people who are closer to the middle or people who are on the other side of average. It gets less and less likely that that sample mean is going to be that same distance, that same 10-point distance from the mean. And if I measured a larger sample, like 20 people, the odds that that sample mean would be a full 10 points away from average start to get very, very slim. You're going to see some exercises in your practice quiz that are going to help you sort of visualize this drop in probability, but basically the exact same raw score difference becomes less and less probable as you measure more and more people, because again, those sample means are going to get closer and closer to the real population mean. It's more unlikely that they're this far apart now that we've measured more folks. So what that means in turn is that measuring more people makes it easier to find statistical significance. The bigger your number of people in your sample is, the less of a difference you need to observe between your conditions to find statistical significance. Let's take an example here, and I'll try to move relatively quickly. The only real way to demonstrate sampling distributions is with tiny populations. So we're going to do a real tiny population here. We have 5 people in our entire population. And in this case, the variable we're measuring is the height of these 5 players who start on a basketball team. Okay, so we've got their individual heights here. This is what we might call our raw score distribution. I want you to pay attention to the range. Notice there's a 10-point difference between highest and lowest individual score. Keep that in the back of your head. Some descriptive statistics, the mean of this population is 80 inches. The standard deviation is 3.81. Watch those numbers as well and how they change or don't change as we turn this into a sampling distribution. So this is our raw score distribution. It makes up our population. Let's say that we wanted to take every single sample with 2 people in it from that population. Essentially, we're making a sampling distribution of the means of samples with 2 people in them. So here's a list of every single 2-person sample that could be drawn from this population. We have their heights. Here we have their mean heights. There's that X bar that we don't see too often, but that's a mean of that particular sample. Notice again the range. The range for the raw scores was 10 inches. But then we look here and we see, okay, the biggest score is 83.5. The smallest is 77. We now have a 6.5 inch range. See how it's compressed a little bit? It's gotten a little bit narrower. They aren't as far apart now that we're looking at sample means of just 2 people instead of individual scores. The distribution's already got a little narrower. So we can demonstrate this sampling distribution as a frequency polygon. This is what it would look like. Notice that's not really a normal curve, but it's not a normal curve. It's starting to get there despite the skew that's definitely present. The mean of that sampling distribution is the same as the mean of the population. It's still 80. If you don't believe me, you can add up all of these scores, divide them by the number of samples, which I believe is 10, and you will get 80 inches. However, the variability has dropped. We'll talk about how we can calculate that later on. Now let's make a different sampling distribution. Let's get a bigger sample size. Let's take samples of 4 people out of our 5-person population. Here's every possible sample, their individual heights, and their average heights. Notice that range has dropped yet again. It's now down to 2.5 inches between the largest sample mean and the smallest sample mean. The same exact raw score differences not only are becoming less common with this very small population when we go to sampling distributions, they're becoming impossible in some cases. It's no longer possible to have a sample mean of 77 inches. It just isn't possible to happen with that population. Again, the mean of this distribution is still 80. You can average them together, you'll find it, I assure you. But the variability has dropped. We're going to figure out how to calculate that momentarily. So here we recap some characteristics of sampling distributions. Every sample is randomly drawn in this theoretical distribution. The idea is that you're drawing all these samples randomly. They all have the same sample size, and that sample size is the same as whatever your real sample is. It's essentially an infinite or very high number of samples. We would calculate the mean for each sample. We take those means, we turn it into a frequency distribution, and again, the mean stays the same of that overall distribution, but the individual sample means get closer and closer as variability decreases. So here's what sampling distributions look like for that same basketball example. This dotted line reflects the population mean. Here's our raw score distribution. Here's our sampling distribution for samples of 2. Notice it's getting narrower. Our samples of 3, notice it's still getting narrower. Those edges are kind of coming in closer. Samples of 4, narrower still. And with a sample of 5, of course, there's no variability. The sample mean must be the same as the population mean. So the mean is constant. The variability is decreasing steadily, and we represent that variability through what's called the standard error. To be continued on that. Again, the mean does not move. We have a little applet here. I'm going to record a bonus video where I'm going to walk you through that applet, but basically what it does is it lets you make simple sampling distributions, and you can see how some of these patterns arise. So again, here's what that all boils down to for our purposes. Because the sampling distribution, its variability changes as you measure more and more people, we have to convert our standard deviation to what's called the standard error, technically the standard error of the mean. Here's the formula. Sigma, remember, is a population standard deviation. We divide it by the square root of the number of people in our sample. Notice that accounts for different sample sizes. That gives us this sigma m, which is the standard error of the mean. So notice the more and more people that you measure, the bigger your denominator will get, and therefore the smaller your standard error will become. Here's a formula for standard deviation. It's the computation, or it's the definitional formula at the population level. Notice again that we need to know the population standard deviation to calculate this standard error. We need that sigma. If we don't have it, we can't plug it in there. What do? To be continued. Our second point of emphasis is that idea of standard error. Again, that distribution of sample means can be mind-boggling, but what winds up happening essentially is you need to know that the variability decreases. Extreme sample means are much less likely as you measure more people. To account for that, we just make that small conversion. We take the standard deviation, we convert it to a standard error. This is really easy to calculate, but forgetting to do it is one of the most common mistakes I see in this course. Anytime you are dealing with sample means, whether it's here or in a hypothesis test, you must convert that standard deviation to a standard error. If you forget to do it, it will hurt you in multiple places. Remember to make that conversion. The formula is going to be right there. So if we have a normal distribution, we know the mean, we know that standard error, we can calculate the probability that a sample mean comes from that population. And the short version is the more standard errors away it is, the less likely it becomes, the more improbable. This is a big step towards statistical significance, but we haven't put it all together yet. Again, when we don't know that information, what do? We usually use a control condition. So for future service, this is going to come up in the next couple of modules. We can use that probability. We can use those z-scores in the sampling distribution to find the likelihood of any score or sample mean. We do that by calculating z-scores. Here we see z-scores for individual scores. Instead, we use this formula that accounts for the sample mean. This is a big step towards that key stat of statistical significance. Again, the most improbable results are going to fall in a designated area that we're going to call the region of rejection. That the size of that area is determined by probability. Results in that area are considered statistically significant. To be continued, please carry on to that sampling distribution demonstration and your practice quiz. See you soon.